All right, good morning, everybody. So those of you who were following the lecture notes may have actually realised that since the last lecture, we're now on track and following my lecture notes, and will do so through to the end of the course now. The first few lectures of the course, the order of the lectures was rearranged a little bit, but we're now back on the pre-programmed course. So today we're going to talk about surfaces, how we describe them, how we approach problems that involve surfaces, how we work out the normal to surfaces in the different ways that we describe those surfaces, and how we work out the tangent planes to those surfaces. And all of this really is preparation for understanding how you do surface integrals, and that will be tomorrow's lecture. We will investigate how to do surface integrals. Interesting. Okay, so a surface is a 2D surface, as the name suggests, which exists in three-dimensional space. So pedantically, of course, a two-dimensional surface can exist in two-dimensional space at all, but then there's nothing very interesting about that. So we are talking about two-dimensional things, two-dimensional membranes existing in three-dimensional space, and typically like everything else in this course, they can be described parametrically or non-parametrically. So an example of a parametrically defined surface would be something like the position vector to a point on the surface is given by two variables, say r and theta, or non-parametrically, where a surface is, for example, simply defined as a scalar value as a function of x and y. So you'll recall when we started looking at doing the integration in multiple variables, I was explaining the point that when you have something which is a scalar function of x and y, that is actually describing a surface as a function of x and y. So we can have surfaces which are described by a position vector, or we can have surfaces which are simply described by something like a function of x and y. And this is, of course, what this says here. So a non-parametric surface is defined in relation to the coordinate system, and a parametric surface is defined in terms of some coordinates which exist in that plane, but for which you either have in your question some defined relationship to your coordinate system, or you have to work it out from the words which are given in the question. Now, one of the key things is the ability to interchange between parametric and non-parametric, and that requires you to understand, or to, there's no understanding required, to recall in particular, spherical polar coordinate system. So here's an incredibly trivial and straightforward example. So we have a surface which is described by x squared plus y squared plus z squared equals 30. So everybody in the room will know that that is a sphere of radius square root of 30. And how would you write that in terms of a position vector to the surface? Okay. So you can do this in terms of x and y and z, but the way to do it is to switch to spherical polar coordinates. So again then, a reminder about spherical polar coordinates: x, y, z. I have some point in my 3D space. The position vector to that point makes a polar angle theta with the z-axis. This point then projects down onto the xy plane, where it makes an azimuthal angle phi with the x-axis. So this means that z, and if the length of this vector is r, this means that z equals r cos theta. x equals the projection of this r sine theta down onto the xy plane, and then projected onto the x-axis, cos of phi, and y is r sine theta sine phi. So this then means that a simple parametric simple parametric expression which describes exactly the same thing as x squared plus y squared plus z squared equals 30 is simply r equals the square root of 30 sine theta cos phi I plus the square root of 30 sine theta sine phi j plus the square root of 30 cos theta k. And you must be able to switch between parametric and non-parametric, which, as I say, will require you, and of course it's very straightforward, it just requires you to remember it, to understand and remember the spherical polar coordinate system. So you'll recall that when we were talking about the Jacobian and changing coordinates, that I gave the example of a part of a circle, and a part of a circle where you can see it in the xy coordinate system. And then when we've taken that circle and we've switched it to an r theta plane polar coordinate system, then it simply becomes a rectangle. And as I told you before, these lines with the different colours represent the same lines projected from xy to the r theta coordinate system. So in particular, you see that this short line here and this longer magenta line are lines of equal length in the r theta coordinate system. So you can do the equivalent visualization for a surface which exists in 3 dimensions. So here is a surface, this is a parametric surface, where the surface is described in terms of 2 parameters, u and v. And again, these are the typical parameters that we use when we have a parametrically described surface, but they're not the only ones, right? You can have any as you like. And so this surface is described by u cos v in the I direction, u sine v in the j direction, plus vk in the z direction. And just in terms of u and v, then we imagine that we have some range going between 0 and 1 and 0 and 2 pi in the v direction. And when we consider that in u and v coordinates, of course, again, this is just a rectangle. That's nice and easy 2-dimensional integration. If we consider what that surface looks like in 3 dimensions, this is what that surface looks like in 3 dimensions. So this surface is rising as a constant function of v, and it's describing a circle. Okay, it's moving around due to v also, and the radius of the circle is u. So if we have a range in u between 0 and 1, then we are filling out the circle. So this is essentially a helix, which is filled from the z-axis. We're filling out the circle, that's the range in u, and it's going right round in 2 pi, which is completing the circle. So, of course, most of what we do is just mathematical manipulations. It's not essential to be able to visualize these things, but it really can help to visualize these things. So you should try and get in the practice of looking at these parameterizations and being able to visualize them. All right. So, to begin our steps towards understanding how to do surface integrals, we need to understand the concept of the vector area. So if I imagine this is some curved surface existing in my 3D space, then what I want to do, again, analogous to how you used to do your normal integrals and now how you do your line integrals and everything else, you break it up into infinitesimal small areas. So we have our surface, and we break it up, we imagine, into many small facets. And when we do the integral, of course, we're taking the limit where those facets become infinitesimally small. For each of these facets, then we take the area of the facet, which is the scalar ds, and we multiply it, or we project it in the direction which is the normal to that surface given by n hat there. Okay. And that is the vector area of our facet. then one of the nice things about the vector area, so once you're able, and we'll come in this lecture on how to do this for any surface, once you're able to work out what the unit normal is to that surface, then you can work out what is the area of your facet projected in any direction. Okay? So we have the vector area of our facet here, ds. ds vector is our unit vector times our scalar area. The dot product of this vector area with any direction tells you about the projection of that area in any given direction. Okay, so you get the maximum value, of course, along the normal, and if you had, for example, direction which was perpendicular to that, you'd see, of course, that you had no projected area at all. So if you have a facet, you get the maximum area. If you're looking at it from the side, you see no projected area at all. And we will use this later on when we are dealing with surfaces to do the trick of taking surfaces which exist in 3D space and projecting them down onto the xy plane so that we can turn surface integrals into 2D integrals in the xy plane. Okay. So there are some important properties of vector areas. So the first important property is that for any curved surface, the vector area is less than the scalar area. Okay? And you can imagine that because if you have a curved surface, this means that in your base coordinate system, you have parts of that surface which are which have components pointing in opposite directions, and so will cancel each other out, and so the sum of your vector area will always be less than the total area of your surface, which is your scalar area. So the second important point then about the vector area is that for a closed surface, the vector area is 0. Okay? So this means that if you have a closed surface, okay, so I have a completely enclosed volume described by my surface, then for every component of every surface element, there is an equal and cancelling part somewhere else on the surface which cancels it down to 0. So the vector area of a closed surface, a sphere, a cube, any geometry you like in 3 dimensions is 0. And then the best one So, in case you can't read that, for an open curved surface, so this is a surface which is not closed, with the same boundary as any other surface with the same open boundary, the vector areas are equal. So let me illustrate what I mean by that. So I have some open surface. So this is a boundary, and the surface in this case exists, the surface exists above this boundary, okay? So I have some surface in here which is delimited by this boundary here, okay? And I can calculate the vector area of this surface. If I have exactly the same boundary over here, then I will find that the vector area of this or any other surface which connects to this boundary is exactly the same. Okay? This is an extremely useful property, and this will, later on in the course, this will allow us to do Stokes' theorem, which is a very valuable theorem. Stokes' law. So, as I've already said, the component of the vector area in some direction, in any direction, is equal to the scalar area of the surface when viewed from that direction. So, in other words, you have your vector area of your component or your surface, you project it, you dot product it with any direction you want, and that tells you the projected area in that direction. Surfaces that share the same boundary have the same vector area, even if they have very different shapes and hence different scalar areas, and this forms the basis of Stokes' law, as I mentioned. Okay, so let's do a straightforward example. Let's calculate the vector area of a hemisphere. Okay, so I have a hemisphere which I'm going to draw badly like this. Okay, so this is my hemisphere. The position vector, let's say it has radius r. So as we know then, our position vector, which describes points on this surface, is a function of theta and phi, my two angles in spherical polar coordinates. Because it's a hemispherical surface, r isn't changing, so it's only a function of theta and phi. So this is r, whatever that radius is, sine theta cos phi I, r sine theta sine phi j, plus r cos theta k. Okay. So, what I want to do first of all is I want to work out what is the unit normal to that surface. So we don't need to do any fancy maths here at all. It's actually very straightforward. You look at this and you think, what's a unit normal to the surface? Well, a unit normal to the surface, very conveniently in this case, a normal to the surface is just given by the position vector of any point on the surface. Okay? So that's very handy. So the position vector which describes the surface is actually a normal. The magnitude of that position vector is r. That's also very handy. So this means that in this case, for a hemisphere or a sphere, or any part of a sphere, then the unit vector is simply sine theta cos phi I plus sine theta sine phi j plus cos theta k. Okay, so now there's another trick where you can use symmetry to simplify your problem. So you'll recall that I was saying that for any curved surface, you'll always have a bit pointing in one direction, which is at least partially cancelled by some other bit which has components pointing in the other direction. So you can imagine in the case of perfect symmetry that that cancellation is perfect. And indeed, this is what happens with the hemisphere. So if you look at this, this is of course symmetric around the z-axis up here. For every point on the surface of this hemisphere, I would have my normal here. I would have some component in the x, y, and z directions. The x and y components, when you integrate around the hemisphere, are going to perfectly cancel. The only thing which is going to be left, for the integral of the vector area of this hemisphere is going to be the component in the k direction. Everything else is simply going to cancel because of symmetry. So this makes my integral very straightforward. So what I want to do then is I want to integrate I want to integrate my polar angle, theta, between 0 and pi by 2. Now, as an aside, people sometimes make the mistake when they're integrating some function over the surface of a whole sphere of saying, well, theta must go between 0 and 2 pi, that's the whole sphere, and phi must also go between 0 and 2 pi. Of course, that's not correct, right? In order to map out the surface of the sphere, you just need half a circle wrapped round. Okay? So a whole sphere would be theta between minus 2 pi by 2 and plus pi by 2, and phi between 0 and 2 pi. In this case, we just have a hemisphere, so we're doing phi between 0 and 2 pi. Okay. Now, we want to integrate our surface area, and we know that it's just going to be projected in the k direction. So whatever our result is here, this is just going to be the component of our surface area in the k direction. So this is going to be ds. Dot producted with the k direction. So in this case, ds is n times the scalar value of the surface area element for a sphere. So n, we know, we have n there, and the dot product of n with k is simply going to be cos theta. So that's very convenient. The surface element in spherical polars, is r squared sine theta d theta d phi. So that's that. So we need to put all of these things in. So our integral becomes the integral of theta between 0 and pi by 2. Phi between 0 and 2 pi of cos theta times by r squared sine theta integrated with respect to d phi and d theta. That's our integrated vector area, which is only going to point in the k direction. So this then tells me that the total vector area is the result of this, which turns out to be pi r squared, and it's projected in the k direction. So my integrated vector area for my hemisphere is pi r squared k. And again, of course, when you think about it, that's no surprise. If you look down on a hemisphere from down the z-axis, which is the k direction, then of course all you're going to see projected in that direction is a circle. So this is the area of that circle that's projected in the k direction. Of course, the nice thing about this, because of what I was saying over there, is that now you know for any curved surface in three-dimensional space, whose base is a circle in the xy plane, you know what the total vector area is, right? Okay. So this works for anything with the same base. Okay, so one of the most important things we need to do then, so in this case it was very easy to find the normal. We just look at the problem and we know what the normal is, it's actually just the position vector. That's of course not the general case for a surface in 3 dimensions, and we need some tricks to work out how to work out the normal. I'm going to show you 2 paths now to working out the normal which give you the same result, so that you understand what's going on. So the first thing is, if we imagine x, y, z again, and I have some function g of x and y, this tells me, as I was saying earlier, that for any point in the xy plane, then I have some point z, which ends up mapping out some surface as a function of the projected position on the xy plane. So this surface is actually a constant surface of a 3D scalar field. So if our surface is essentially, what we're saying is our surface is z is g of x and y, that's an equipotential or a constant surface of a three-dimensional scalar field, which is given by z minus g of x and y, which you can see is 0. So this is just an equipotension of our 3D scalar field. You'll recall that we discussed this previously when we were discussing the gradient and had some figures. So now we know that we have a 3D scalar field. We know from previous lectures that the gradient then of this field will give us a normal to that surface, to that equipotential. So we work out what is the gradient of f, our 3D equipotential. So our gradient of f is going to be minus I dg by dx minus j dg by dy plus k. Okay. So I've just worked out the gradient of this 3D scalar field, which describes our surface. So I have the gradient. This isn't obviously unit normal, but this is a normal to the surface, and of course I could flip all the signs, and that also gives me a normal to the surface, the normal pointing the other way out of the surface. And so my unit normal then to this surface is given by, I'll write it around this way, k minus I dg dx minus j dg dy, all divided by the square root of 1 plus dg dx squared plus dg dy squared. So that's my unit normal to any, hopefully it's the same as what's written there. Yeah. So that is the unit normal to any non-parametric surface which you're given in a question. There is an alternative way of reaching the same result. Okay, so this is, this hopefully is that expression. Yeah, that is the same expression. Now, yeah, so I'll make the note now. This looks a bit nasty, but of course it's, you know, there's nothing in here which is particularly complicated, but it's nasty because it's got several terms and a square root and etc. This part, as you're going to see, nearly always cancels out when you're doing your problems, okay? And in fact, the same thing happens when you're doing parametric problems as well. It's very nice, so this part will normally cancel, and I'll show you that later on in the lecture. There is another way of arriving at the same result. So, if we imagine now that we have some curved surface existing in x, y, z in three-dimensional space. If we choose two vectors which lie in the surface, which lie in the plane of the surface, we call those u and v, then we see if we move a small amount, so u and v lie in the plane, and we see that if we move a small amount in the x and y directions, which we'll call ux and vy, then the vectors in the surface become I times ux. There's no component, we've chosen two orthogonal vectors here to make it simple. There's no component in the y direction, but because this is a 3D surface in three-dimensional space, there may be a component in the k direction, so that would be k times ux times the rate of change of my function with x. And similarly, my vector in the v, the y direction, would be j times my small change in that variable plus k v y dg dy. So I now have two vectors which are in the plane of my surface. So of course, in order to get one route to get a normal is to take the cross product of those two vectors, which will give me a normal to the surface. So a normal to this surface is u cross v. So that's I, j, k. U has an I component of ux, no j component, and a k component of ux dg dx. And this one has, that's 0, 0. This one has 0, Vy, and Vy, dg, dy. So this equals then minus I dg dx minus j dg dy plus k all times ux vy. So that's a normal to the surface. You can see that we're going to end up with the same result. And of course, a unit normal to the surface is my u cross v divided by the magnitude of u cross v. And when we divide our cross product by its magnitude, this ux vy here is going to cancel out. So that disappears. So we end up again with the same result, which is k minus I dg dx minus j dg dy all over the square root of 1 plus that squared plus that squared. So this is how to work out the unit normal to a non-parametric surface. This is the expression that you would use. In the case that our surface is given parametrically, then our position vector r will be some function of u and v, such that our x-coordinate will be a function of u and v, we don't know what it is. Our y-coordinate will be a function of u and v, we don't know what it is. And our z component will also be a function of u and v, and we don't know what that is either. Again, what we want, following the same method which we applied here, is we want two vectors which are in the plane of that surface, and those two vectors are the rate of change of the position vector with an increase in the parameter u, and the rate of change of the position vector with a change in the parameter v. These two are vectors in the plane. So therefore, for a parametric surface, excuse me, for a parametric surface, the unit vector is given by dr du cross dr dv divided by the magnitude of this. And I'll show you at the end of the lecture how again these terms cancel out to make our surface integrals more straightforward. And in tomorrow morning's lecture, we'll actually go through some examples of how you do this. So the reason that you're learning these tools is so that you can do surface integrals, and being able to do surface integrals is a big component of this course and allows you to do some of the more interesting theorems that we're going to do at the end of the course. One of the other things, however, that you can use these tools to do is to work out what are the tangent planes to a surface at a given point. So if I have some 3D surface existing, this is not going to work, okay. That's a 3D surface which is existing, which has some curved contours that may or may not look like that. Then you can imagine some point on this surface, and you want to work out what is a tangent plane to that point. So what that means is if that is the normal to the surface at that point, the tangent plane, fortunately I have a graphic coming up, the tangent plane is the plane which is lying in the surface at exactly that point. Okay. So the tangent plane is the three-dimensional, it's the surface equivalent of the tangent to a normal curve. So we want to use the tools that we've learned to be able to calculate tangent planes. There we are. So there's a better graphic. There's a sphere. There's a point on the sphere. just been discussing here, one of our general methods for calculating the normal to the surface. And then we use the fact that the dot product of the normal and a vector in the plane must be 0. Okay, so you'll recall way back, I think in the first lecture, we briefly recapped how you work out the equation of a plane. And one of the ways you do it is if you have a vector which is normal to that plane. So we'll go through an example of that now. This is something which comes up periodically and is important for you to be able to do. All right. So let's find the equation of the tangent plane to a parametric surface, which is given by this expression here. So we have a surface position vector as a function of u and v is given by ui plus 2v squared j plus u squared plus v. And we want to find tangent plane at x, y, z equals 2, 2, 3. Okay, so we have a parametric description of our surface. So what we want to do is we want to use the method here, just above, to work out what is the normal to our surface. So the first thing we do then is we want to work out what is dr du. So dr du is I, there's no j component, plus 2uk. That's one vector which is lying in the surface in the tangent plane. And we want dr dv, which equals no I component 4vj plus k. What we want to do now is we need to take the cross product of these two vectors, which we know lie in the surface at that point, which means they also lie in the tangent plane at that point. We want to take the cross product of these two, so that gives me I, j, k, 1, 0, 2u, 0, 4v, 1. And that equals minus 8uv in the I direction, minus j plus 4vk. Right, now we need to consider that we're evaluating this tangent plane only at this point 2, 2, 3. We don't want a general expression for the tangent plane, we want to evaluate it at a specific point. So at 2, 2, 3, we know that the position vector is given by our original expression for our plane. So we know that the position vector is given by this expression here, or the expression that's written there on the slide. So that immediately tells us, since I, which is the term in front of I is u, that's the x coordinate, we see that at this point u equals 2. Now we see that 2v squared equals 2. So that means that v squared equals 1, but that's a little bit annoying because that means that we cannot tell whether v equals plus or minus 1. But we see that z, which is 3, equals u squared plus v. And we know that u equals 2, so u squared is 4. And we know that the z coordinate at this point is 3, so that tells us that v equals minus 1. So then we know that our normal to the surface at this point is given by 16i minus j minus 4k, putting in our values of u and v, which we've worked out for this point. So working out the tangent plane, we don't need a unit normal, we just need a normal to the surface at a given point. And our equation for working out the tangent plane then is x minus x0, which is the coordinate at which we're evaluating it, times the x component of our normal, plus y minus y0, our y coordinate, times the y component of our normal, plus z minus z0 times the z component of our normal equals 0. That's the equation of our tangent plane. And if you put all of these things in, then you see that you get an expression 16x minus y minus 4z equals 18. That's the tangent plane to the surface described by that parametric expression there at the point 223. So it's all very straightforward. It's just a question of turning the handle and grinding through the maths. Okay. One of the key tricks that we use in solving surface integrals, as I was mentioning previously, is instead of trying to integrate over our surface in three-dimensional space, we use the fact that the vector area dot producted with a given direction allows us to project that area into a certain direction. So what we do often, not always, what we do often is that actually when we're solving our surface integrals, if this is the surface here, we project it down onto the xy plane, and that then allows us to tackle our surface integral, which exists in 3 dimensions, as a 2-dimensional integral projected down onto the xy plane. And what happens then is that you have some element of surface here, ds, which you want to do your surface integral over, but that actually projects down onto some shape on the xy plane, which you can then just describe in terms of x and y, which makes it much easier to do your integral. Now, if you're projecting down onto the xy plane, then you're taking the dot product of your vector area with the k direction. So we're taking the dot product of this vector area with k to give us the projected area down onto the xy plane. So what we say then is we say that this is ds. We call this dA. Typically what we will do is we will say that we are describing this surface by S and this surface by D. So again, as I mentioned, repetitively throughout the course, the trick is you're changing your function, you're changing your coordinates. The projection term, as we'll see in a moment, is very straightforward, okay? That's very straightforward, and beautifully it cancels with our normalization term for our normal, as we'll see in a moment. The trick often is to see how this area that exists in 3 dimensions, what the limits are of that when you project down onto the xy axis. So we know that our unit normal to some given surface is given by k minus dg dx in the I direction minus dg dy in the j direction, all divided by that 1 plus that squared plus that squared. But if we look at the projection of this normal now, just in the k direction, then it gets much more simple. That simply becomes 1 over the square root of 1 plus that squared plus that squared. And that equals the ratio of our area projected on the xy plane to the actual area in the surface. Okay? So what that means is actually, and perhaps this is not such a surprise, our projection of our area from our surface down onto the xy plane is adjusted by a factor which is the same as the normalization of our normal to the surface at that point. So that means that when we're rewriting our integral, which initially is always in terms of ds, we are taking ds and we are replacing it with this term, 1 plus square root of dg dx squared, square root of dg dy squared, dA. And dA will typically be dx dy, because we're evaluating in the xy plane. So we're going to go through tomorrow some examples, so this will embed a bit more clearly in your heads. But the nice thing about this then, as you can probably intuit, is that this is going to cancel with our normalization term. We can do the same thing for parametric surfaces. The projection for a parametric surface, where we're evaluating it in the surface, is simply given by this expression here, and this expression is equivalent to the Jacobian. Okay, so let me just quickly go through how this simplification occurs, and then we'll see this in action in the lecture tomorrow. So for a typical surface integral, you will have the question that describes some surface S. It's a surface that's an integral in 2 dimensions of some vector times by n.ds, which is our vector area. Okay, so that's how you frame your initial problem. If we take this and if this is in so if I take a non-parametric case, what I do is I take my surface and I project it down onto the xy plane. So D is my projection now down onto the xy plane. I take the dot product of whatever my field is I'm evaluating my vector surface integral over, and I have my unit normal at that point. So my unit normal at that point, as we've now done repeatedly, is k minus I dg dx minus j dg dy, all divided by 1 plus squared plus squared. But I also then want to replace ds, which is my unit area on my surface in 3 dimensions, with dA, which is my unit area projected down onto the xy plane. So ds then becomes, as I've just shown over here, it becomes this same term, dA. And then beautifully, what you get is that this and this cancel out. So just to be explicitly clear, what I'm talking about here is D is the area of your surface projected down onto the xy plane. That requires a bit of thought. And dA is typically, if you're projecting onto the xy plane, would be dx dy. You may, of course, project onto other planes, and you'll get problems like that as well. But the correction factor for the surface projection exactly cancels the normalization of the unit vector. So that means that these problems become much, much simpler. And I will leave it there, and we'll go through some real examples tomorrow. Thank you.